So here we are in ethers and epoxides, which is chapter 14 in the current textbook we use. But it's ethers and epoxides. It goes along with alcohols. It's the sp3 hybridized oxygen doing some work. But an ether, we can name it either of two ways. We can name it by what's on one side of the oxygen, the ethyl, what's on the other side of the oxygen, the methyl and ethyl, and then follow it up with ether. Or we can do it with, as the smaller of the two groups, making it a methoxy off of the longer one 1-methoxybutane. Okay. Now ethers are slightly different than an alcohol in that the alcohol has the hydrogen on the oxygen. The ether has two alkyl groups. So what happens is, since the alcohol corresponding molecular weight for all three of these roughly is the same, the ethanol has the hydrogen bonding availability of the hydrogen on the oxygen, so the boiling point is much higher than either the dimethyl ether or the propane, because there isn't a hydrogen to hydrogen bond too. So how can an ether help us? If we were to make it a Grignard, we all know some of us have done the Grignard reaction in lab, where you used some alkyl bromide, magnesium metal, and ether solvent. And the ether solvent complexes the metal cations to help stabilize it and help it form in solution. We can do this with different crown ethers, and a crown ether is just a cyclic ether with carbons and oxygens in it, with a 2-carbon chain in between the two oxygens, no matter which size it is. So we have the 12 crown 4, 15 crown 5, and the 18 crown 6 as 3 examples of this, and the smaller one solvates the lithium, the medium one the sodium, and the bigger one the potassium, and it's just the perfect size to fit within the cavity of the molecule. Okay. So how much will we use the crown ethers in this class? Not very much, but if you go on to other things, you need to know that it is a possibility. So the reaction of potassium fluoride with 1-bromooctane and benzene will not occur without the addition of the crown ether. The fluoride ion is not soluble in benzene and will not react without the 18 crown 6. So that makes it all possible to make the 1,4-octane. So preparation of an ether, how can we do it? We can start with ethanol and add acid and slight heating, and we can get it to form the diethyl ether by first protonating the alcohol from the sulfuric acid, and then another equivalent of ethanol comes in to displace the water leaving group, and then we remove the hydrogen off of the ether with our ethanol that we have lots of to make the diethyl ether. Okay, believed to undergo in an SN2 since it is a primary leaving group, but it works. If we're use too much heat, we'll end up pushing it to eliminate instead of doing the substitution. So there is a line we have to be careful of as we do that. The better way to make an ether is by taking off the hydrogen with a strong base off of the alcohol to make the ethoxide, and then do an SN2 on a primary leaving group to make in this case, the diethyl ether. And yes, it needs to be a primary one. If you have a secondary one, secondary halides and tosylates are sometimes used, but the yield is depressed. Why? Well, remember what we learned in Org 1. If you have a strong base and a secondary leaving group, you run the risk of either it being a substitution in SN2 or an E2 reaction. So this, on a secondary, is either SN2 or E2, and we have to, depending on the conditions, we're going to get some of both. And we can't keep one or the other from occurring. So here we have some reactions. Can we predict the product from it? If we add sodium metal, and remember, when we write just Na, we're talking to sodium metal with an alcohol, it's going to form the alkoxide, and it's going to make hydrogen gas, which is going to bubble out of solution and be gone. Once we form the alkoxide, it's going to do an SN2 on our alkyl halide to make, in this case, the methyl ether. It just depends on what we have the bromide on for what it could do. In the second case, the sodium hydride is a strong base. It's going to remove the hydrogen off of the alcohol, giving us the alkoxide, and then the alkoxide can react with methyl bromide to form the ether, 2-methoxy 2-methyl-butane. Okay, nothing to it. And the third one, remember we said on the previous page that the leaving group needs to be a primary or a methyl leaving group. If it's not a primary or methyl leaving group, other reactions can occur, and we have to be careful what we want to have happen. So if we take sodium hydride and add it to methanol, we get methoxide, which is a very strong base, and methoxide reacting with a tertiary bromide is not going to do a substitution. It's going to do the elimination, and we're going to get the alkene out of it and methanol. Okay, so we have to be careful which way we go about doing these to force it to do the substitution as opposed to the elimination. So what kind of reactions have we already learned? Okay, back in Org 1 and Chapter 6, Chapter 7 and 8, the additions to alkenes, we had mercury acetate and water, and we formed an alcohol. Here we have mercury acetate and methanol, so instead of forming an alcohol, we're going to form the methyl ether because the methanol adds to the three-membered ring mercury as opposed to water in the one we did before. So we have to be careful what is our solvent. It doesn't matter what it is. The solvent, whatever is the nucleophile in the solvent, will add to the more substituted carbon in this reaction. We can cleave an ether by reacting it with acid, HBr, protonate the ether, and then the bromide can come in, do an SN2 to form the ethyl bromide and ethanol, and then the ethanol can go grab another hydrogen off of the HBr, and then another Br minus can come in and displace it, and we end up forming two equivalents of the ethyl bromide, or an equivalent of each side of what the ether was to start with. So can we draw the mechanisms with methyl phenyl ether? So we can protonate it. We know the bromide can come in and attack the carbon of the methyl, kicking out the phenol. So that gives us methyl bromide and phenol. Now, when we're at the phenol, yes, we can protonate it. But once we protonate the phenol, is there anything we can do to this carbon of the aromatic ring? And we know, we were told early on in Org 1, in any of the reactions we do, until we get into the aromatic section in Org 2, do not touch the aromatic ring because we haven't learned the reactions. An aromatic ring has vastly different reactivity, takes special reactions to do anything. So all we can do with this is to remove the extra hydrogen to get back to phenol and the methyl bromide. And we learned in Org 1 that to do a SN1, SN2, E2 or E1, what type of carbon with a leaving group on it? We needed to have an sp3 hybridized carbon to do any of those reactions, because an sp2 hybridized carbon is not reactive towards, especially the substitution reactions. Will not do anything with them. So here we have the aromatic carbon there, which is an sp2 hybridized carbon. It's not reactive to a simple substitution reaction, so nothing will happen there. If we have an epoxide, how do we name it? It's an epoxy pentane. So we have 5 carbons. The epoxy is on carbons 2 and 3, so it's a 3-ethyl 2-methyl 2,3 epoxy pentane. Or we can name it as the oxyrain with what's off of it. You got 2 ethyls and 2 methyls, 1,1 diethyl, 2,2 dimethyl oxyrain. Either of those are fine ways to name one of these. So how can we make an epoxide? We learned in Org 1 that a acid, a carboxylic acid with an extra oxygen in it, a per acid, reacts to form the 3-membered ring. And how does it do that? Well, the pi bond attacks the oxygen of the per acid, the one connected to an oxygen. It kicks out the leaving group, the carboxylate. The carboxylate grabs the hydrogen off of the other oxygen, and then that bond breaks to form the epoxide. So when we do this, whatever the stereochemistry is of the alkene, it is conserved in the reaction. So this is a cis-alkene. We get the 2 methyls on the same side. The trans-alkene, the 2 methyls are on opposite sides. Whatever the stereochemistry of the alkene, it is conserved in the reaction. The preparation of halohydrins, bromine and water, we've drawn that mechanism before. It gets bromine on the less, the oxygen on the more substituted carbon of the double bond. They are anti to one another, and then once we're there, we can remove the hydrogen off of the oxygen to make the alkoxide, and then do an SN2, since the oxygen's anti to the bromine, to form the 3-membered ring. Okay. For this to occur, both groups have to be in the axial position. Okay, just like we learned back in Org 1 in the chapter, the nucleophile, to do anything on the cyclohexane, the leaving group has to be axial in position so that we can do something to the atom next to it. So we can open up the ring either of 2 ways once we make that epoxide, and we've drawn this multiple times. With acid, this oxygen of our acid ends up being the oxygen on the more substituted carbon of what was the epoxide. If we add base and have hydroxide, that oxygen ends up being on the less substituted carbon, because this is basically a straight SN2 mechanism, and in an SN2 mechanism it always adds to the less substituted carbon. Okay, so the mechanism for that SN2, the hydroxide comes in, we break open the 3-membered ring, we have this intermediate with the oxygen with a negative charge, and we just have to go grab a hydrogen off of the water, and we have our product, the anti-diol. Okay. And anytime we have a 3-membered ring, if we have a strong nucleophile, the strong nucleophile is always, whatever it is always going to add to the less substituted carbon. So if we add hydroxide, it adds to the less substituted carbon and tied to the leaving group. If we added any of these things, they would all do the same sort of thing. Add on the opposite side of the leaving group and on the less substituted carbon if the carbons are different. So how can we draw this mechanism with acid? We can protonate the oxygen of the epoxide, and then our water adds to the more substituted carbon, breaking the epoxide at the more substituted carbon. The water that adds comes from the opposite side of the leaving group, so it came from the front side, and then another water comes in to take off the extra hydrogen, and we get to our product of having the anti-diol. And we can add different nucleophiles for this also. It's just comes down to having the positive charge in the three-membered ring in that intermediate, that the nucleophile we add once we're there is always going to add to the more substituted carbon. So thiols and sulfides, we know sulfur is just below oxygen in the periodic table, so oxygen and sulfur, for a simple organic chemist's point of view, they're going to do everything basically the same. There's a little bit difference, but the types of reactions they do are going to be basically the same. So when we had an alcohol, this would be 3-methyl-1-butanol. If we change it to a thiol, it's 3-methyl-1-butane thiol. So all we do is add the thiol at the end instead of over here we added the alcohol. If it's a substituent off of something, then it's a 3-mercapto, 3-methyl-1-butanol. No, that's all. So how can we make one? If we have a primary leaving group, we can do a simple SN2 to make the thiol. Sulfides are analogous to ethers. So a diethyl ether, diethyl sulfide, the naming is the same. Okay. The one thing I should have said about sulfides and thiols is they smell bad. Sulfur smells bad when it's in an organic molecule. So you have to be, if you're working with a sulfide, you have to be very careful as you work with it. So here we can do another SN2 with the thiol. Simple reactions. We've done tons of these. You can do these. So, synthetic strategies. If we start with an alkane, what can we do to it? If we needed to make this, if we were told to make that anti-disubstituted alkane, okay, how would we get there? If we started with an alkane, we've said all along in organic, the only thing we can do to the two things we can do to an alkane, we can burn it and we can brominate it. There's nothing else really we can do with an alkane. An alkane is very unreactive. So we start with the alkane. The only thing we can really do to it is brominate it to make the tertiary bromide, then do the E2 elimination to make the alkene, and then we can make the epoxide to put the oxygen on there. Yeah, we get both enantiomers of it, the oxygen going back, the oxygen coming forward. We're just carrying on through the one we're looking for to get the oxygen where we want. And then to that, we can add acidic methanol to it, protonate the three-membered ring, and then the methanol adds to the more substituted carbon. So it adds to the carbon on the back and all, and it would give us this product. And in this, from starting with an alkane, all we can do is brominate it. So this is the first step in anything where we have to turn an alkane into anything else. The first thing we're going to do to it is brominate it. Okay. So if we're looking at this, we have said all along there are two things we can do to a Grignard, or add a Grignard to, I guess I should say. We can add it to a carbonyl, or we can add it to an epoxide. Those are the only two things we can add a Grignard to. So the Grignard R minus, if it adds to a carbonyl, the R, the bond we're forming, is bonded to the carbon that has the oxygen on it. Okay? That's the bond we form in the Grignard reaction when it's connected to the carbon that has the alcohol on it. We had to add that to a carbonyl of some sort. If the bond we form is not connected to the carbon that has the oxygen on it in the end, the only thing we can add that to is an epoxide, because in the mechanism the Grignard comes in, attacks the three-membered ring, and opens it up, so the oxygen ends up on carbon 2 of that epoxide. So if they're not connected, the only way to make that is by adding a Grignard to an epoxide. Whatever epoxide, whatever the two carbons that were on of the epoxide, whatever is attached to them would have to be on the starting epoxide. Okay, so this is the only two things we can do for any of these reactions with a Grignard. We can add it to a carbonyl, we can add it to an epoxide. That can add a Grignard or an alkyl lithium too. So here we see we have a carbon with a bromine on it, and we need to form this bond between the cyclohexyl and the carbonyl. So we're forming a bond that goes to the atom with the oxygen off of it. So the only thing we have to do is make a Grignard and then add into that Grignard a 3-carbon aldehyde, because the Grignard is bonded to the carbon that has the oxygen on it. And then after we add acid to it to make the alcohol, we add PCC, because we want to oxidize it up to the ketone. That sense, we're forming this bond here that's connected between the carbon that was the Grignard and the carbon that was the carbonyl that we added it to. Okay. Now, if the carbon of the Grignard is not connected to the carbon that has the oxygen on it in the product, this is the carbon with the oxygen on it, this is the carbon of the Grignard, there's this CH2 in between, the only way we can do this is to make the Grignard and add it to an epoxide, so that the Grignard adds to that little red carbon, and the oxygen stays on the little blue carbon here. Okay? Because as the Grignard adds, it adds into the carbon that has the red dot, breaking the CO bond off of it. So the oxygen ends up staying on the carbon that has the blue dot, and then we add water to make the alcohol and then oxidize it with PCC, and we get the ketone. This is the only two ways we can add a Grignard to either a ketone or an epoxide, or a carbonyl and an epoxide are the only two things we can add a Grignard to. So here we have the predicted products for all the different reactions in alcohols and ethers. So if we have the mercury acetate and methanol, we're going to get the methyl ether. If we have a primary alcohol in a not too high of heat, we get the ether. If we have a secondary one and we reflux it, we're going to get the alkene. If we have an ether, we're going to get two equivalents. In this case, where the both sides of the ether are equivalent, we're going to get two equivalents of ethyl bromide. In the next one, we have the aromatic ring with the oxygen off of it. We can't do anything to that. We're going to get phenol out of that. And then we're going to get the methyl bromide. MCPBA makes the epoxide. So we get the three-membered ring with the oxygen in it. And then with acid, it opens up to the more substituted carbon. With base, it opens up to the less substituted carbon. So and then chlorine and water gives the anti-addition of the chlorine and the alcohol, and then we make the epoxide. Okay. It's not the greatest way to make one, but it will work. So can we draw some mechanisms? Can we draw a mechanism reacting 1-propanol with sulfuric acid and slightly elevated heat to make the ether? So the first thing we do is protonate the alcohol, and then another propanol comes in and displaces it to make the protonated ether, and then another propanol comes in to remove that hydrogen to get us to the neutral ether. If we add sulfuric acid to a secondary alcohol, we protonate to make the protonated alcohol, turn it into a good leaving group. It leaves, forming the cation, and then the water we just formed can go grab a hydrogen and form the alkene to give us the double bond. If we add the ether, so we protonated the ether, it gives us the protonated ether. We add bromide in to one of them, displace the ethanol leaving group. That gives us an ethanol and an ethyl bromide. The ethanol goes and grabs a hydrogen off of HBr to give us another protonated oxygen with a positive charge, and the second equivalent of bromide can come in and displace it to give us our second ethyl bromide. And we drew that earlier in this section also. And then the last page here is what can we do with the epoxide. Okay, if we add the strong base, we know it adds to the less substituted carbon to give us the O minus on the more substituted carbon, the methoxy on the less. The O minus will go grab a hydrogen off of the acid solution to get us to the product. If we have an acidic solution of the epoxide, we'll redraw it so we can see everything. We protonate it first with the acidic methanol, and then methanol adds to the more substituted carbon of the three-membered ring to give us and open up the three-membered ring to give us, I ran out of space, sorry, this, and then we take the extra hydrogen off with another methanol, and that gives us our anti-addition. Here, chlorine, we tack a chlorine, we form the three-membered ring chloronium ion. Oops, better be consistent. With the chlorine going back, and then water adds anti to the chlorine to give us, whoops, chlorine, remove the extra hydrogen, and we have the anti-addition of the chlorohydrin. and then hydroxide can come in and grab the hydrogen off of the hydroxide of the alcohol. That gives us a O minus chloride, and then do an SN2 on that, and that gives us the epoxide. Okay, so it's another way to make an epoxide. Not as good as the epoxidation with the peracid MCPBA, but it does work. So there's that. Okay, so those are all of the reactions for the alcohols and ethers and epoxides. If you have any questions about any of them, feel free to send me an email. Okay. We've done all of these many times. You should be able to draw them without a problem. If you have a question, send me an email and we can talk about it. Have a good weekend.